Welcome to another deep dive, and today we've got, well, a paper all about knots. Effective bounds on characterizing slopes for all knots. I think this will be a fun one.
Yeah, knot theory is full of these really interesting geometric problems.
And this one is about trying to figure out if we can pinpoint the exact identity of a knot just by looking at how it changes after we do a certain kind of modification.
Yeah, it's like, can we modify a knot? And then, based on what we end up with, know exactly which knot we started with.
So it's about finding a unique fingerprint for every knot.
Exactly.
That's pretty cool. So first things first, what does it even mean for a slope to be characterizing for a knot?
Okay, so picture a knot, right, like in 3D space.
Okay, got it.
Now imagine we drill a hole right through it, following the path of the knot. So we've got this tunnel.
All right, I'm visualizing that.
Then we take a solid torus, basically a donut shape, and glue it into that tunnel.
Okay, so we're filling the tunnel with a donut.
Exactly. And the way we glue it back in, well, that's determined by a fraction, PQ. This fraction basically describes the slope. And this whole process, it's called Dehn surgery. It gives us a new three-manifold.
A new three-manifold, okay.
And the question is, can we look at this new manifold and know with absolute certainty which original knot we had? If the answer is yes, then that specific PQ, that slope, is called characterizing for that knot.
I see. So it's like we're trying to use this surgery to encode the knot's identity.
Exactly.
Now, this paper, it doesn't just look at specific knots. It aims to find a way to calculate these characterizing slopes for any knot.
Yeah, that's the big goal. Patricia, Sorya, and Wakelin, they wanted to come up with a universal method. A lot of previous research had focused on specific types of knots, but they were aiming for something much broader.
So their approach could apply to any knot you can think of.
Exactly. And their main tool is this concept of JSJ decomposition.
JSJ decomposition. I'm not familiar with that. Can you explain?
Sure. It's a way of breaking down a knot's exterior, the space around the knot, into simpler pieces. It's like taking apart a complicated machine to examine each individual part. And the idea is that these pieces, they hold the key to figuring out these characterizing slopes.
So by analyzing the parts, we learn about the whole.
Yeah. And their main result, Theorem 1.1, it connects this JSJ decomposition to a certain bound. They call it CK.
CK, okay. And how does this bound help us find characterizing slopes?
Well, it basically says that if the denominator of our slope fraction, if it's bigger than this bound, CK, then we can be absolutely sure that the slope is characterizing. It's like a guarantee.
So it's like a test. If the slope passes, it means it uniquely identifies the knot.
Exactly.
Now, it doesn't end there, right? Because Theorem 1.2 introduces three more constants, QK, RK, and SK.
Right. Each of these constants, it comes from some specific geometric property of the hyperbolic pieces in the JSJ decomposition. And Theorem 1.2 says that if our slope's denominator, Q, is bigger than all three of these constants, then we're guaranteed a characterizing slope.
Okay, so we've got these three hurdles our slope has to clear. Can you give me a bit more intuition about what each constant actually represents?
Sure. So let's start with QK. Imagine you're trying to find the absolute shortest loop you can create within a specific hyperbolic piece.
A loop within one of the pieces. Okay.
Right. And QK is related to the length of this shortest loop. It's kind of like trying to find the tightest belt you could wrap around that piece.
Ah, so it captures a kind of fundamental length within that piece. What about RK?
RK has to do with the twistiness of the pieces that aren't on the outermost part of the knot. It measures how intertwined things are in that particular section of the knot's exterior.
So it quantifies a kind of complexity within the knot. And lastly, SK.
SK is similar to QK, but instead of just one hyperbolic piece, it looks at all the hyperbolic pieces that aren't touching the boundary of the knot itself. You could think of it as finding the shortest path that spans across all those inner pieces.
So it gives us a sense of how interconnected those inner pieces are. These constants, they really give a detailed picture of the knot's geometry, don't they?
Definitely.
But hold on a sec. How do we know that when we try to match these surgered manifolds, that it actually respects this JSJ decomposition? Like, what's stopping us from just randomly gluing the pieces back together?
That's a great question, and that's where Proposition 1.7 comes in. It's crucial because it basically says if we have a homeomorphism that's like a structure-preserving mapping between two surgered manifolds and the denominator of our slope, Q, is big enough, then this homeomorphism must respect the JSJ decomposition.
So it's like a rule book for matching, making sure we're staying consistent with the knot's structure.
Exactly. It makes the whole matching process really rigorous.
Okay, so proposition 1.7 makes sure we're playing by the rules. But then there's also this mention of winding number 0 patterns and theorem 1.8. What's that all about?
Ah, that's a bit more specialized. Theorem 1.8 deals with a special case where all the ways we can describe the knot as being built around another knot, the pattern always has a winding number of 0.
Winding number of 0. What does that even mean?
So imagine a thread representing the pattern, and it's woven around a core knot. The winding number basically tells you how many times that thread goes around the core before connecting back to itself. A winding number of 0 means it might weave back and forth, but it never fully encircles the core.
Okay, so it's interacting with the core, but not fully binding it.
Right. And for these special knots, Theorem 1.8 gives us an even more refined bound for characterizing slopes.
Even more refined. So easier to figure out which slopes uniquely identify these knots.
Exactly. And it all comes down to a new constant they introduced, TK, which is all about the twistiness of the companion knots in this winding number 0 situation.
So TK helps us zero in on the characterizing slopes with even more precision. That's pretty amazing.
Yeah.
But all of this is quite theoretical. Do they actually show how these concepts work in practice?
They do. In section 5 of the paper, they have some concrete examples. They use a software tool called Snappy, which is specifically designed for studying 3 manifolds, and they use it to calculate these bounds for specific knots.
So they walk us through how to apply this framework to real knot analysis.
Yeah, they show that it's not just theoretical, it's actually quite practical.
This is all very cool. So to recap, we've got a system for characterizing slopes based on this JSJ decomposition, 3 geometric constants, and then a refined bound for knots with those winding number 0 patterns. It's quite a lot to take in. But what I'm really curious about is, where do you think this research leads? What's the bigger picture impact?
Well, I think it gives us a really strong foundation for future research, both in knot theory and in 3-manifold topology. I mean, the bounds they've established, the tools they've developed, they open up so many possibilities for classifying knots, understanding their properties. Who knows, maybe even applications in other areas of math and physics.
It feels like we're just scratching the surface. I'm excited to dig into the actual proofs and see how they build their arguments.
Me too.
Yeah.
And the proofs are quite elegant. They really demonstrate a deep understanding of knot theory.
Well, I'm ready if you are. Let's dive into the details of Proposition 1.7 and see how they actually prove this crucial part of their argument.
All right, let's do it.
Okay, so Proposition 1.7. This is where they actually prove that the matching has to respect the JSJ decomposition.
Right, exactly. It's all about making sure that any matching between these surgered manifolds, it truly reflects a genuine structural match between the knots according to their JSJ decompositions.
Right, so no, just like randomly shoving the pieces together.
Well, right, exactly.
So just to recap, what exactly is Proposition 1.7 claiming?
Okay, so it says that if we have a homeomorphism, which is like a mapping that preserves the structure, between the surgered manifolds of 2 knots, K and K prime, and if the denominator of our surgery slope, that's the Q, is large enough, then this homeomorphism can't just map pieces randomly. It has to align the surgered pieces of K with the corresponding surgered pieces of K prime.
So it's got to respect the decomposition. Like, how do they actually go about proving that?
Well, they use proof by contradiction. They basically analyze all these different scenarios and show that if the homeomorphism didn't respect the JSJ decomposition, we'd end up with impossible situations.
So they start by assuming the opposite of what they want to prove. And then they show that that assumption leads to a contradiction.
That's right.
Okay, so what are some of the scenarios they consider?
So first, they focus on the JSJ piece of the second knot, K prime, which they call Y prime.
Okay, Y prime.
And they start by showing that Y prime can't be the exterior of a torus knot.
Why not?
Well, if it were the exterior of a torus knot, then the surgered manifold that you get from it, Y prime of P over QT prime squared, that wouldn't have any JSJ tori. So it would be missing some of the structure you'd need to match up with a knot that had a hyperbolic piece.
Ah, I see. It'd be too simple.
Exactly.
So no torus knot exteriors for Y prime. What's next?
Well, then they look at the case where Y prime is a composing space, meaning the surgered manifold of K prime would contain the filling of a composing pattern, that's s cubed p prime of p over qt prime squared.
Composing patterns, those are basically the patterns that connect two knots together, right?
Yeah, you can think of it as like linking two knots.
Right.
Now, if our homeomorphism isn't mapping the surgered pieces directly onto each other, this filling of the composing pattern would have to be homeomorphic to the exterior of some other knot.
So we'd be saying that a piece that's supposed to be linking two knots actually looks like the exterior of a separate knot.
Right. But they use a previous result, lemma 5.4, from one of the first author's earlier papers, to show that this can't happen when the denominator of our slope, q, is bigger than 1.
So for most cases, we can rule out composing spaces as a potential match for y prime. Okay, that narrows things down a bit. What other scenarios do they look at?
Well, once they've ruled out torus knot exteriors and composing spaces, they're basically left with two main possibilities. Either y prime is a hyperbolic space, meaning it has this characteristic non-Euclidean geometry, or it's a cable space, which is a space you get from winding around another knot, kind of like a cable around a cylinder.
Okay, so two main contenders. How do they handle those?
So for the hyperbolic case, they use two of the geometric constants we talked about earlier, sk and slx.
Right, sk comes from all those inner hyperbolic pieces of our original knot k.
Yeah, the ones that aren't touching the boundary of the knot. And SLX, that's a value we get from the systole of a specific hyperbolic piece. The systole, basically, it's the shortest possible loop you can create within that piece. It's a fundamental measure of the piece's geometry.
So sk is kind of a broad view, and slx is zeroing in on a specific piece.
Right. And what they show is that if we choose the denominator of our slope, q, to be bigger than both 25 and any of the SLX values for those inner hyperbolic pieces, then we run into a contradiction.
A contradiction. So this scenario can't actually work.
Exactly, because in this scenario, the filling of our potential hyperbolic piece, y prime of p over qt prime squared, it just can't be homeomorphic to any of those inner hyperbolic pieces of our original knot k.
So the pieces can't match up if their geometries don't match up.
Right. And they use some pretty powerful tools from hyperbolic geometry, including the sixth theorem and this concept of a universal area bound, to establish these constraints.
Wow, so they're using these really abstract geometric concepts to actually rule out possibilities.
Yeah, it's pretty neat how it all comes together.
But what if we do find a match, but it's not a direct match? Like the pieces match up according to the JSJ decomposition, but maybe they're not mapping directly onto each other? Is that where the cable space scenario comes in?
Yes, that's exactly right. So if y prime is a cable space and our homeomorphism isn't directly aligning those surgered pieces, it means that a certain part of K prime's surgered manifold, which should have this cable-like structure, actually ends up looking like the exterior of a torus knot, which they call S cubed J embedded within S cubed K.
Hold on, I need to picture this. So we're saying that a section of K prime's surgered manifold, which is supposed to be cable-like, resembles the space around a torus knot.
Exactly. And this leads to the realization that our original knot, K, it can actually be described as a satellite knot, where the pattern, P, is wrapping around this torus knot, J, as its companion.
Like we're uncovering a hidden satellite structure within K.
Precisely. And because we assumed that K is not a graph manifold, meaning it has at least one hyperbolic piece, this pattern, P, it must also contain a hyperbolic JSJ piece, which they call X.
Okay, so torus knot J inside pattern P, and P has a hyperbolic piece X. This is getting pretty intricate.
It is. So what happens next is they look at what happens if the homeomorphism doesn't directly map the surgered pieces. This means that the JSJ torus, which is like the boundary between S cubed J and the rest of S cubed K, gets mapped by the homeomorphism to the boundary of y prime of P over QT prime squared with an S cubed K prime of P over Q. And this boundary, it also defines the exterior of another torus knot, J prime, this time within S cubed K prime.
Okay, so we have these two torus knots now, J and J prime, linked by this homeomorphism. What does this tell us about K prime?
Well, it means that K prime must also have a satellite structure, which they write as P prime of J prime, where P prime is the pattern for K prime. So basically, we've swapped the roles of the pattern and the companion between K and K prime.
Like they're trading places?
Exactly. And the really cool thing is that Sorya and Wakelin show that this swapping can't happen if the denominator of our slope, Q, is bigger than the constant RK.
RK, the twistiness constant.
Yep. And they prove this by doing a clever trick. They perform a specific filling of the pattern space, S cubed P. They choose this filling very carefully so that they can use a previous result from the first author's work, Proposition 5.8, from their 2024 paper on characterizing slopes for satellite knots.
So they're building on their previous research.
Exactly. And this specific filling of S cubed P, together with the fact that Q is bigger than RK, it leads to a contradiction based on a fundamental theorem in knot theory, the cyclic surgery theorem.
So again, they show that the proposed matching doesn't actually work.
Right. So they successfully handle both the hyperbolic and the cable space scenarios, showing that any homeomorphism has to respect that JSJ decomposition.
So they basically eliminated all the possibilities where the homeomorphism wouldn't align with the decomposition. That's a pretty big step.
Definitely. Proposition 1.7 is a really solid foundation for the rest of their proof.
So where do they go from here? What's the next piece of the puzzle? All right, so we've got proposition 1.7 under our belts. It seems like a pretty big deal for their main argument. What's next in their journey to proving this theorem 1.2?
So with proposition 1.7, they've established that any homeomorphism, any mapping that preserves the structure between those surgered manifolds of our two knots, K and K prime, has to respect that JSJ decomposition, meaning it has to map the surgered pieces, y of p over q to t squared and y prime of p over q to t prime squared, onto each other.
So the pieces line up according to the decomposition, but how do we know that y and y prime are actually the same?
Well, that's where proposition 3.3 comes in. Yeah. This proposition says that if the denominator of our surgery slope, that q, is larger than q of k, which remember has to do with the shortest loop in a specific hyperbolic piece. Well, if q is bigger than q of k, then y and y prime have to be the same JSJ pieces.
So it's not enough for them to just line up. They've got to be identical pieces, like fitting together puzzle pieces, but not only the shapes have to match, but the images too.
Exactly. And to prove this, they really carefully go through each possible JSJ piece type, ruling out any inconsistencies. They draw on some results from their earlier work too.
Meticulous analysis seems to be a recurring theme here, and a deep understanding of the foundations of knot theory.
Absolutely. Their expertise really shines through in these proofs. But there's one more potential wrinkle they have to address. What if K and K prime are cable knots? Meaning they're formed by winding around another knot. That could mess things up.
Right. Cable knots can be tricky. How do they deal with that?
Well, here they use this really clever idea of cosmetic surgeries. These are Dehn surgeries on a knot that are different, but they result in the same three manifold.
So it's like wrapping the same present in different paper. The outside looks different, but it's the same gift underneath.
Exactly. And by considering these cosmetic surgeries, they show that if K and K prime are cable knots, they have to be cable knots of the same underlying knot, which they call K hat.
So they have this common core, even if they look different on the outside.
Right. And this, together with their previous results, leads to their big conclusion. K and K prime must be the same knot. They started with the seemingly simple question, can we characterize knots based on their slopes? And ended up building this whole framework with these geometric constants and logical arguments to give a definitive answer.
What a journey. It's really amazing how they weave together all these complex ideas to arrive at this powerful result.
It really is a testament to the elegance of mathematical reasoning.
Now, earlier you mentioned Theorem 1.8, which gives a refined bound for certain types of knots. Can you remind me what makes these knots special?
Sure. Theorem 1.8 focuses on satellite knots, where no matter how you describe them as a knot built around another knot, the pattern always has winding number 0.
So no matter how it's wrapped, the pattern never makes a full loop around the other knot.
Right. And for these particular knots, Sorya and Wakelin show that you can find an even more precise bound for characterizing slopes.
More precise. So it's even easier to determine which slopes uniquely identify those knots.
Exactly. It's like having a finer-grained measuring tool. And the key to this refined bound is this concept of splicifiable knots.
Splicifiable knots. What makes a knot splicifiable?
So imagine you have a satellite knot, K, made up of a pattern, P, and a companion knot, J. If the pattern P has winding number 0, meaning it doesn't fully encircle the companion, and the pattern itself is unknotted, and you can unknot the companion knot, J, by performing a specific type of modification called a null-homologous Rolfson T-twist. Then K is what we call T-splicifiable.
Well, hold on. Break that down for me. What's a null-homologous Rolfson T-twist?
Basically, it's a way of adding twists to a knot, but in a way that doesn't fundamentally change its topological properties. The T in T-twist just refers to the number of twists you add. It's kind of like putting curls in a ribbon, but without cutting or gluing it.
So for a splicifiable knot, you can basically untangle it by adding a certain number of twists to the companion knot.
You got it. And proposition 4.2, which is another big result in this paper, it establishes this connection between splicifiable knots and the swapping of JSJ pieces that we were talking about earlier.
You mean that situation where the homeomorphism could swap the roles of the pattern and the companion?
Exactly. They show that this kind of swapping can only happen if the knots involved are specifiable, and the specific number of twists it takes to unknot the companion that actually dictates the slopes at which the swapping can occur.
So knowing whether a knot is specifiable and what its t-value is tells you something about its characterizing slopes.
Exactly. And because of this link between specifiable knots and non-characterizing slopes, they show that for any knot, there's a limit to how many twists you can add and still be able to unknot it using this null homologous Rolfson twist.
So there's a point where no amount of twisting will untangle the knot. Interesting that there's a limit like that.
It is, and this leads to the definition of a new constant, T of k, which is the largest possible t-value for which the knot k is specifiable.
So tk basically measures how untwistable the knot is.
I like that. And then proposition 1.9 brings it all together. It says that if the denominator of our slope q is bigger than both 2 and T of k, then any homeomorphism between the surgered manifolds must map the surgered pieces directly onto each other.
So it's similar to proposition 1.7, but specifically for these winding numbers 0 knots.
You got it. And this leads to the proof of theorem 1.8, which says that for these special knots, if q is bigger than both q of k and T of k, then we're guaranteed that the slope p over q is characterized.
It's a refinement of theorem 1.2, where r of k and s of k are replaced with t of k, so they could be a much smaller bound.
Exactly. And Sorya and Wakelin actually go on to show that in certain cases, this refined bound is the best possible bound, meaning there are knots where if q is less than or equal to T of k, you can find a homeomorphism that doesn't directly map those surged pieces. And they give some really cool examples to illustrate this, which shows how powerful this result is.
Wow. We've covered so much ground. We started off trying to understand what makes a slope characterizing, and we ended up exploring all these deep connections between knot structure, geometric constants, even the limits of untangling knots.
It really highlights the beauty and complexity of knot theory.
It certainly does. This deep dive has definitely expanded my understanding of knots. Thanks so much for guiding us through this amazing paper. It's been a real pleasure.
The pleasure is all mine. Thanks for joining me on this mathematical adventure.
Welcome back to another deep dive. You know, we love to dig into mathematical proofs, and today, oh boy, do we have a fascinating one for you. We're going to be exploring how some geometric properties, and you might not expect this, can actually be used to identify and classify mathematical knots.
And it really comes down to this idea of characterizing slopes, you know? It's like, imagine you've got a knot, any knot, and picture drilling a tube-shaped hole straight through it.
Okay, I'm visualizing it. Got my knot, got my drill.
All right, so now you glue that tube back in. But here's the twist, literally. You glue it back in with a twist, and the amount of twisting you do, well, that slope can actually tell us exactly what the original knot was, at least in certain cases.
So we're talking about using Dehn surgery, right?
Yeah.
And using that to analyze, what, all kinds of knots?
Yeah, pretty much. This paper goes deep into how Dehn surgery results can point back to the original knot type. We're talking everything from torus knots to hyperbolic knots.
Oh, and don't forget those crazy satellite knots, cable knots, and composite knots. Those are always fun to wrap your head around.
You said it. But the main goal here, the big question this paper is tackling, is to find a specific value. It's a sort of limit. They call it CK for any given knot.
Okay, I'm following so far. CK for any knot. All right.
So if we twist more than that CK during Dehn surgery, the resulting shape, well, it could only have come from that one specific knot K. It's like each knot has its own breaking point.
Whoa. Each knot has a unique breaking point. That's wild.
And what's even cooler is that geometric properties of a knot, like its systole, actually play a big part in determining this CK value.
Hold on, remind me, what's systole again? Is that like the shortest loop you can wrap around the knot?
You got it. It's like using geometry to unlock the secrets of topology.
That's mind-blowing. So let's break down this characterizing slope idea a bit more. We denote it with, what was it, PQ, and it's specific to a certain knot K, right?
Exactly. And if we do Dehn surgery using this specific slope, it produces a three-manifold, a shape that's unique to that specific knot. It's a one-to-one relationship, like a signature.
Wait, so only that specific knot with that specific characterizing slope can produce that exact same three-manifold?
Got it.
But how do you even prove something like that? Where do you even start?
Well, it gets really interesting here. We have to break down the knot exteriors, the spaces around the knots, into simpler pieces using something called JSJ decomposition.
Okay, hold on. Knot exterior. Can you quickly remind me what that is again?
It's basically everything around the knot itself. Imagine a knot just floating in 3D space. The knot exterior is everything but the knot. It's like the space the knot lives in, but not the knot itself.
Right. Okay, I remember. So we break down this knot exterior into smaller parts, simpler shapes, using the JSJ decomposition. It's kind of like taking apart a machine to understand all the little pieces, right?
Exactly. And each of these pieces fits into a specific category. Some parts resemble torus knots, others look like cable knots, composite knots, or even those hyperbolic knots.
And then theorem 1.1 comes into play, right? This is where the paper says that the geometry of those pieces, those individual parts we just talked about, is what determines that important CK constant.
Exactly. Theorem 1.1 essentially tells us that we can actually calculate how much twisting a specific knot can take before it loses its signature. And that calculation depends entirely on the shapes of those decomposed pieces.
Wait, so you mean the shape of those basic parts of the knot dictates how much you can twist it before it's not unique anymore? That's incredible.
It is pretty amazing. Now, to really get how this theorem works, we need to zoom in on the most complex part, those hyperbolic pieces.
Oh boy, the hyperbolic pieces. Always a fun time. And now we're adding two new constants, RAK and SK, to the mix. This is where I start to get lost.
No worries. Think of RK as a measure of how stretched out things are inside the hyperbolic piece. It's based on the lengths of these lines called meridians within that crazy shape.
So RK is telling us about distances inside the hyperbolic piece.
Yeah, you could think of it that way. Now, SK is a bit different. It's tied to the systole of the hyperbolic piece. Remember, the shortest loop. So SK is more about the overall tightness of that piece.
Okay, so RK is about how stretched out things are inside, while SK is more about the overall tightness. Is that a fair way to put it?
Exactly. You nailed it. And these two constants, they're essential for understanding how Dehn surgery affects these hyperbolic knots. Remember, the whole point of the proof is to show that if we twist enough more than that CK value, the pieces stay distinct. They can't get mixed up between different knots.
So no matter how much we twist them, those pieces stay unique. Kind of like a puzzle where each piece can only fit in one specific spot.
Exactly. But proving that, that's where the real mathematical heavy lifting comes in.
I bet. So where do we go from here? What's next?
Well, the paper then focuses on a specific type of knot. Those satellite knots where the pattern has a winding number of 0. Picture like a vine wrapping around a tree branch, but it doesn't make a full circle. That's essentially what 0 winding number means for satellite knots.
Okay, so we've got this special type of satellite knot where the pattern doesn't fully encircle the companion knot. What makes them so special in all of this Dehn surgery stuff?
Well, Theorem 1.8 suggests that for these particular knots, there might be an even tighter limit, even better than CK, to determine when Dehn surgery gives us a truly unique result.
So it's like these 0 winding number satellite knots have this extra layer of precision when we try to identify them with Dehn surgery.
Exactly. And the paper suggests that this tighter limit depends on how much twisting it takes to unknot the companion knot, the one that's sort of inside that satellite structure.
It's like untangling a knot within a knot. How do they even measure something like that?
Well, that's where things get even more interesting. We have to dive into this concept called the maximal null homologous Rolfson twist coefficient. It's a bit of a mouthful, I know, but it's a fascinating idea that helps us refine our understanding of these special satellite knots.
All right, lead the way. I'm ready to dive into the world of twist coefficients.
Okay, so imagine you're trying to unknot a knot by making twists. So imagine you're trying to unknot a knot, but you're doing it by making twists along a specific unknotted loop, one that doesn't actually link with the main knot itself. We call these null homologous Rolfson twists.
Okay, so it's like you're making a twist in this separate loop that's kind of woven into the knot structure, but not directly around the main knot.
You got it. And the fascinating thing is, for certain knots, there's a maximum number of these special twists you need to completely unknot them, that maximum number. Well, we call that the maximal null homologous Rolfson twist coefficient. It's a mouthful, we just call it TJ.
So TJ basically tells us how many twists of this specific type it takes to undo a knot, right? But how does this all tie back to those special satellite knots with a 0 winding number?
That's the brilliant part. For a satellite knot, we define this new constant, TK, which is the biggest TJ value among all its possible companion knots. So we're looking at all the J's.
Okay, so we're essentially finding the companion knot that's the toughest to unknot, and then using its twist coefficient to, what, put a better limit on when Dehn surgery can uniquely identify the whole satellite knot.
That's a great way to put it. Now, calculating this TK, well, it can get pretty tricky. But there are some types of knots where it's relatively easy. For example, there's a whole class of satellite knots where TK is actually 0.
Wait, 0. So you can't unknot those companion knots no matter how many of those special twists you do? What kind of knots are those?
The paper describes them in Corollary 5.6. Basically, these are satellite knots where no matter how you describe them as this combo of a pattern and a companion knot, they're never splicifiable.
Hold on, splicifiable. Now I'm picturing genes or something. What does splicifiable even mean when we're talking about knots?
Think of it this way. It means the companion knot can be unknotted by making just one single null homologous Rolfson twist. But these specific satellite knots, they're kind of resistant to that no matter what companion knot you pick.
So they're tangled up in a way that you just can't untwist them with this specific method. Wild. And because TK is 0 for these knots, we can simplify CK down to just QK rate.
You got it. And there are tons of knots that fit this description. A classic example would be a satellite knot, where the companion knot has a large signature.
Hang on, signature, like signing your name. What does that even mean for a knot?
It's a mathematical property of a knot, something that relates to its topology. It's like a way to measure some aspects of the knot's structure. And the interesting thing is, if a knot has a big enough signature, specifically if its absolute value is greater than or equal to 4, then you can't unknot it with just one of those special twists.
So knots with big signatures are kind of unspecifiable because they just refuse to be untangled that way. That makes sense.
Exactly. And Corollary 5.8 points out that for satellite knots, where all the companion knots have a big signature, we can refine that bound, CK, down to just QK. And remember, QK is based on those hyperbolic pieces of the knot exterior, something we can actually calculate fairly easily.
This is so cool. It's like we're using different properties of these knots to figure out these boundaries for when Dehn surgery can reveal their true nature.
It's a great way to think about it. And while calculating that TK can be a real pain in general, there are some cases where it's not too bad. For instance, there are these satellite knots where the companion knots are either composite, meaning they're made by joining two knots, or they're fibered, which means they have a specific layered structure. For these types of knots, that TK value is at most 1.
So even if they are splicifiable, it takes at most one of those special twists to unknot them.
Exactly. And Corollary 5.10 tells us that this means we can actually refine CK down to QK for those knots as well. It's another situation where Theorem 1.8 gives us a more precise limit, which often ends up being smaller than the bound we get from Theorem 1.2.
It's like finding these shortcuts, these more efficient ways to figure out a knot's identity based on its Dehn surgery results. But you said earlier that the bound from Theorem 1.2 might not be the best possible. Is the refined bound from Theorem 1.8 always optimal?
Not always, but in some specific cases, it is. This happens when a satellite knot is always splicifiable no matter what companion knot you choose, and that TK value is greater than or equal to QK.
So we have a knot that's always untwistable, with a certain number of those special twists, and that limit happens to be bigger than that QK value. What does that mean for our bound in those cases?
It means we've hit the jackpot. Corollary 5.14 tells us that for these knots, if you twist more than TK during Dehn surgery, you're guaranteed to get a shape that could only have come from that specific knot. And you can't find a better, more precise bound than that.
That's amazing. We've gone from this seemingly impossible task of identifying knots based on Dehn surgery to finding these precise limits, these characterizing slopes that unlock a knot's true identity.
It really highlights the power of the math we're using and the beauty of connecting geometry and topology in these unexpected ways. And what's even more exciting is that there are still so many open questions and avenues to explore in this area.
That's what I love about math. It's always more to discover. But before we get ahead of ourselves, let's walk through a couple of specific examples to see how these optimal bounds actually work in practice.
Absolutely. Let's look at a specific type of knot called a multi-classed Whitehead double. Basically, it's a Whitehead link that's been twisted and kind of interwoven multiple times. It's denoted as WNTMT.
Okay, so we have this pretty complex knot structure based on this twisted and interwoven Whitehead link. And our goal is to figure out the best possible bound for when Dehn surgery gives us that unique result, right?
Exactly. And what's interesting about these multi-classed Whitehead doubles is that they're always splicifiable. This means their companion knots, which are noted as TMT and are actually double twist knots, they can always be unknotted with a certain number of those special twists we've been talking about. And we know that for these double twist knots, that maximal null homologous Rolfson twist coefficient, that TMT, it's greater than 1.
So they're always untwistable with those special twists, and it takes at least 2 twists to do it. What's the next step to finding that optimal bound?
Well, we need to figure out the exact value of TK for these knots. Luckily, we have this awesome tool, an algorithm by Mark Lackenby, that lets us calculate that TMT precisely, which in turn gives us our TK.
So we use Lackenby's algorithm to find out exactly how many twists it takes to unknot that companion knot, and then we compare that to QK, which we can figure out from the hyperbolic pieces of the knot. It's like a mathematical showdown.
That's a great way to think about it. And in example 5.15 in the paper, they show that for certain choices of M, N, and T in that WNTMT structure, you can actually make TK greater than or equal to QK. And this puts us right in that sweet spot where corollary 5.14 kicks in and TK becomes the best possible bound we can find.
So if we twist more than that key K value, the one we got from Lackenby's algorithm during Dehn surgery, we know for sure that we'll end up with a shape that could only come from that specific multi-class Whitehead double, and we know there's no better, more precise bound out there.
That's the power of this result. It gives us this precise, optimal way to identify these complex knots based on their Dehn surgery results. And the best part, this is just one example. There's a whole universe of knots out there just waiting to be explored using these tools and techniques.
It's mind-blowing to think that we can use these abstract mathematical ideas to pinpoint something as concrete as a knot's identity. It really shows how elegant and powerful mathematical thinking can be.
Absolutely. It shows that even in something as seemingly simple as a knot, there are layers and layers of complexity just waiting to be discovered, and the beauty of it all. These discoveries often lead to even more questions and deeper insights, pushing our understanding further than we ever imagined.
It really shows how powerful math can be, right? Connecting things that seem totally different, like geometry and topology, to figure out these fascinating objects.
Yeah, and it shows us that even in a field like knot theory, something that's been studied so much, there are still so many things we don't know, so many mysteries to uncover. This research, it really opens up this whole new way of thinking about how the geometry of a knot, those basic pieces, can actually reveal what the knot truly is.
We've gone over a lot today. I mean, from characterizing slopes and JSJ decompositions to systole, winding numbers, and even those crazy twist coefficients. So for our listeners out there, what's the big takeaway? What should they be thinking about after this deep dive?
The key thing to remember is this. Mathematicians, they've found this way to use the geometry of knots, the stuff that's already there, to know exactly when Dehn surgery can be used to identify a knot. It's like we've cracked some kind of code, found a whole new language for understanding the hidden structure of these things.
And what's really amazing is how these ideas, they might seem abstract, like the shape of those tiny pieces of a knot, or the shortest loop around it, or even how many twists it takes to untangle a companion knot, all of that stuff. It plays such a crucial role in identifying the knot itself. It's like a perfectly orchestrated piece of music.
This research, it opens up so many possibilities. It hints that there might be these deep connections between geometric properties and topological properties, things we haven't even begun to fully grasp. Makes you wonder what else is out there, hidden in plain sight, just waiting for us to discover it.
It's wild to think that even something as basic as a knot can hold so much complexity mathematically. It reminds us that learning is this constant journey, and there's always something new to learn, even in the most familiar things. Thanks for joining us on this deep dive into the world of knot theory. We'll see you next time. All right, let's dive into this paper. Effective bounds on characterizing slopes for all knots.
Okay.
I know you're well versed in knot theory,
Yeah.
so we can skip the intro to knots and get right into it.
Sounds good.
Okay.
To me, characterizing slopes are a fascinating concept. The idea that a single surgical slope could uniquely identify a knot.
Exactly. It's like a topological fingerprint.
Yeah, like a fingerprint.
Yeah, so the paper jumps right into Dehn surgery. I'm assuming our listener is familiar, but just as a quick reminder, it's how we modify a 3-manifold by cutting out a solid torus and gluing it back in with a twist.
Right, and that twist is where the slope comes in.
Okay.
Formally, for a knot K in the 3-sphere, Dehn surgery along K with slope PQ, where P and Q are coprime integers, gives us a new 3-manifold denoted S3PK.
So PQ dictates how we glue that torus back in. Now, the big question is, can the result of this surgery, S3PK, pinpoint the original knot K?
Precisely. That's what makes a slope characterizing if no other knot could produce the same manifold through Dehn surgery with that same slope.
It's been proven for some simple knots. The unknot, trefoil, figure 8.
And interestingly, for those, every rational slope is characterizing, but things get more complex as the knots themselves get more intricate. That's where this paper makes its contribution tackling the problem for all knots.
And their big breakthrough is showing that a bound exists. There's a limit on how complex the slope needs to become characterized.
Exactly. Theorem 1.1 states, for any knot K, there exists a constant CK, such that any slope PQ with QCK is a characterizing slope for K.
That CK, though, depends on something called the knots JSJ decomposition.
Yes.
I'm guessing that's going to be important.
Absolutely. JSJ decomposition is about breaking down a knot's exterior, the space around the knot, into simpler pieces, each with a specific geometric type. Think of it as a 3D puzzle where the pieces are things like Seifert fibered spaces or hyperbolic manifolds.
So JSJ decomposition reveals the knot's underlying geometric structure. And this structure, somehow, relates to how complex a slope needs to become characterized.
Precisely. Now, the paper doesn't just stop at proving the existence of this bound, CK. Theorem 1.2 goes further, providing an explicit formula to calculate it.
So we're not just left wondering if a bound exists. We actually have a way to find it.
Exactly. But there's a catch. Theorem 1.2 applies specifically to prime knots whose exteriors aren't graph manifolds.
So we're narrowing our focus a bit. Prime knots meaning they can't be decomposed into simpler knots. And this graph manifold exclusion, what's the significance there?
Graph manifolds are a specific type of 3-manifold built by gluing together Seifert fibered spaces along tori. Excluding them ensures that the knot's exterior has a certain level of geometric complexity, which is crucial for the formula to work.
So for these knots, prime, not a simple graph manifold. How do we calculate CK?
The formula involves finding the maximum of 3 geometric constants, Q, K, R, K, and S, K. Each of these is rooted in the hyperbolic geometry of the knot's JSJ decomposition.
Hold on. Hyperbolic geometry? I thought JSJ decompositions could have pieces that aren't hyperbolic.
That's true. But the constants QK, RK, and SK are specifically calculated based on the hyperbolic pieces of the decomposition. They capture key geometric properties of those pieces.
So even though the knot's exterior might have non-hyperbolic parts, these constants zoom in on the hyperbolic bits, and the largest of these 3 gives us our magic CK.
Exactly. And as we go through the details of QK, RK, and SK, you'll see how intricately they're tied to the shapes and sizes of those hyperbolic pieces.
All right, I'm ready to delve into the geometric heart of these constants. Let's start with QK. What's the story there? So let's unpack QK. It feels like we're about to get into the nitty-gritty of hyperbolic geometry here.
We are.
Okay.
QK is defined in a piecewise way.
Okay.
Depending on the nature of a specific JSJ piece, the one that contains the boundary of the knot exterior.
Okay.
For a cable knot, it's the piece containing the boundary of the companion knot's exterior.
So it's focusing on the piece most intimately connected to the knot, so to speak.
Exactly.
Okay.
Now, if this piece is hyperbolic, we use definition 1.3 from the paper to calculate QK.
Right.
QK equals 6 plus 16 over cis LX.
Okay, we've got cis LX popping up the systole of the link exterior. Reminder, that's the length of the shortest closed geodesic in that hyperbolic piece.
Right.
So QK gets larger as the systole gets smaller.
Precisely.
Okay.
A smaller systole means the hyperbolic geometry is more tightly packed, which for some reason necessitates a larger bound on the slope to guarantee its characterizing.
Fascinating. What if that key JSJ piece isn't hyperbolic?
Then QK takes on a different value. If it's a Seifert fibered space with base orbifold S2 to 3T, meaning a sphere with 3 cone points of orders 2, 3, and T, then QK is simply 1.
Okay, so a much smaller bound in those cases. What's the intuition there? Why is QK so small for these specific cipher fibered pieces?
It likely has to do with the relatively simple structure of these ciphered fibered spaces.
Okay.
They don't have the same degree of geometric complexity as hyperbolic pieces, which translates to less stringent requirements for a slope to be characterizing.
Interesting.
Yeah.
It seems like the type of geometry at play really dictates how we approach this problem. Now, what about RK? How does that constant come into the picture?
RK is defined in definition 1.4,
Yeah.
and it deals specifically with those hyperbolic JSJ pieces that have 2 or more boundary components.
Ah, so we're zooming in on those hyperbolic pieces that are connected to multiple other pieces in decomposition. What's the geometric significance there?
It has to do with how those pieces are glued together along their boundaries.
Right.
Remember, the JSJ decomposition cuts the knot's exterior into pieces, and those pieces are joined along tori.
Okay.
RK captures information about those tori, specifically the length of the meridians of the link components associated with the hyperbolic piece.
Okay, meridians, those loops that go around each component of the link. So RK is measuring something about how those components are situated within the hyperbolic piece and how it connects to the rest of the decomposition.
Exactly.
What's the formula?
It involves a maximum taken over all hyperbolic pieces, x, with at least 2 boundary components.
Okay.
RK equals the maximum of 2 plus 4 pi squared over lmx squared.
So again, a connection to hyperbolic lengths.
Yeah.
A shorter meridian length means a larger RK.
Exactly.
And
the geometry of those connections influences how easily different knots could be confused after surgery.
this is really highlighting how the fine details of the knot's geometry affect these bounds.
Yes.
Now on to the last piece of the puzzle, SK. What makes it different from KK and RK?
SK considers all hyperbolic JSJ pieces,
Oh.
as defined in definition 1.5,
Right.
except the one containing the boundary of the knot exterior, in
Yeah.
a sense.
Yeah.
It's looking at the inner hyperbolic geometry of the knot, whereas QK focused on the piece most directly connected to the knot itself.
Okay, so we're shifting our attention to those hyperbolic pieces that are more internal to the knot's structure. How do we calculate SK?
It's another maximum taken over all such hyperbolic pieces, X. SK equals the maximum of SLX.
And SLX, that was defined earlier, right? It has to do with the syftole, the link exterior, but with a bit of a twist.
Exactly.
Right.
It's defined as follows.
Ah.
SLX equals the maximum of 6, 4 pi squared over cis LX squared.
So it's taking into account both a fixed value of 6 and a term based on the systole, the link exterior, similar to what we saw in QK and RK. So SK is like a combined measure incorporating information about the systoles of all those inner hyperbolic pieces and comparing them to this fixed value of 6.
Fascinating.
Indeed.
Okay.
And what's remarkable is that by combining these three seemingly disparate geometric constants, QK, RK, and SK, we get this powerful tool, CK,
Right.
that allows us to determine characterizing slopes for a vast class of knots.
It's like we've distilled this intricate geometric information into a single number that tells us something profound about the knot's identity.
That's a great way to put it.
Yeah.
These constants are more than just abstract mathematical quantities. They're deeply connected to the fundamental nature of knots and how they interact with the space around them.
This deep dive has been quite a journey so far. We've explored Dehn surgery, JSJ decompositions, and now we've delved into the heart of hyperbolic geometry to understand these constants, QK, RK, and SK.
Yeah.
It's amazing to see how these pieces fit together. All right, we've got a solid grasp of how CK helps us find characterizing slopes, but the paper doesn't stop there. It dives into a special case.
Yeah. Knots with winding number 0 in their satellite descriptions. What's the significance of that?
It allows for a more refined approach.
Okay.
Theorem 1.8 introduces a potentially tighter bound for characterizing slopes in these cases.
So instead of always relying on CK,
Right.
which as we've seen can be quite large depending on those hyperbolic geometry constants, we might have a more efficient way to find those special slopes.
Exactly. The key here is the concept of splicifiable knots.
Okay.
These are knots that can be described as satellites, where the pattern has winding number 0,
Right.
and the companion knot can be unknotted by a specific type of modification called a non-homologous Rolfson twist.
Okay, lots to unpack there.
Yeah.
Let's start with splicifiable knots. It sounds like we're building knots from other knots.
That's right.
Okay.
A satellite knot is essentially formed by tying a knot, called the pattern,
Yeah.
into a tubular neighborhood of another knot, called the companion.
Ah, so it's like threading a knotted loop through the hole of a donut
Yeah.
where the donut itself is already knotted?
That's a good analogy.
Okay.
Now, the winding number in this context is
Yeah.
a measure of how many times the pattern knot wraps around the companion knot.
I see. So a winding number of 0 means the pattern isn't really winding around the companion in the traditional sense. It's more like it's woven through it in a way that doesn't create that classic helical wrapping.
Precisely.
Okay.
In the second part of the definition, the null homologous Rolfson twist
Right.
refers to a specific way of modifying the companion knot. It involves performing unassigned desurgery along an unknot embedded within the knot's exterior.
Hold on. Edising desurgery. That sounds familiar.
Yeah.
It's like what we do in Dehn surgery,
Mm-hmm.
but applied to an unknot within the knot's exterior.
Exactly. And testing here represents the number of twists we introduce. So we're essentially twisting the companion knot in a very specific way. The key is that for a splicifiable knot, this twisting for some value of Dehn can completely unknot the companion.
So a splicifiable knot is one that can be constructed using a companion that can be untwisted in this particular way.
Yes.
How does that help us find characterizing slopes?
Proposition 4.2 provides the link.
Okay.
It states that if we have a homeomorphism between the results of Dehn surgery on two knots, and this homeomorphism swaps the surgered pieces.
Way swaps the surgered pieces. Remind me what that means.
It means the homeomorphism matches the surgered solid torus from one knot to a different JSJ piece in the other knot's decomposition, not to its corresponding surgered piece.
Oh, right. It's like the homeomorphism is crossing the wires of the surgery. Okay.
And Proposition 4.2 says this crossed wires scenario can only happen if both knots are splicifiable. Furthermore, those surgeries must correspond to a specific Rolfson twist that unknots the companion.
Okay, so this proposition significantly restricts the situations where that swapping can occur. It feels like we're cornering those characterizing slopes.
We are. And this leads to Corollary 4.6, which states that for any non-trivial knot, there's a maximum number of twists via a null homologous Rolfson twist that can unknot it.
So there's a limit to how much we can untwist a knot using this method.
Fascinating.
It is.
Okay.
And this leads to the definition of TK, the maximum of all those maximum twist numbers for any companion used to describe K as a splicifiable satellite.
So TK is like a measure of how untwistable the companion knots are in the splicifiable descriptions of K.
Precisely. And with TK, we get proposition 1.9.
Right.
If we have a homeomorphism between the results of Dehn surgery on two knots using the same slope PQ with Q greater than the maximum of 2, TK, then this homeomorphism cannot swap the surgered pieces.
This mirrors proposition 1.7.
Yeah.
But with a different bound, instead of the maximum of RK-SK, we have the maximum of 2 in TAK, and it's all thanks to this splicifiability property.
Exactly. And the proof of theorem 1.8 follows a similar path to theorem 1.2.
We've ruled out the swapping scenario. Now we use previous results about JSJ decompositions and cosmetic surgeries to show that the two knots must be identical.
So for knots with that winding number 0 property, we have a refined, potentially tighter way to find characterizing slopes. And it all hinges on this intricate dance between splicifiability, Rolfson twists, and this maximal twist number, TK.
It's a beautiful example of how understanding specific structural properties allows us to develop more precise tools for analyzing knots.
This entire deep dive has been incredible. We've gone from Dehn surgery basics to the complexities of JSJ decompositions, hyperbolic geometry, and now this world of splicifiable knots and Rolfson twists. It's amazing how interconnected it all is.
Knot theory is full of these surprising connections. It's a field that constantly rewards exploration.
What strikes me is that the paper focuses on sufficiently complex slopes. It makes you wonder, could there be simpler characterizing slopes out there?
That's a great question.
Slopes that don't require these intricate bounds.
Perhaps there are hidden shortcuts waiting to be discovered that could lead to even more elegant ways to fingerprint knots.
This has been a truly enlightening journey. I'm sure our listeners, with their expertise in knot theory, have gained even deeper insights from this exploration.
Until our next deep dive, keep those mathematical minds engaged, keep questioning, and keep unraveling the beauty of knots.
Welcome back, everybody, for another deep dive. Today we've got something pretty cool lined up, especially for all of you math enthusiasts out there.
Absolutely. We're going to be talking knots, and not just any knots. We're delving into the world of Dehn surgery, a fascinating technique that lets us explore these intricate little structures by, well, kind of surgically modifying them.
Exactly. And that's where things get really interesting, because with Dehn surgery, we can transform a knot into different three manifolds.
And that raises a pretty intriguing question. Can we actually identify a knot just based on the result of Dehn surgery? Like if we perform the surgery and end up with a specific three-manifold, can we work backwards and definitively say, aha, that must come from this particular knot?
That's exactly what we're diving into today. We're looking at a paper called Effective Bounds on Characterizing Slopes for All Knots by Patricia, Sorya, and Wakelin. And spoiler alert, the answer is a resounding yes. There are specific ways we can use Dehn surgery to pinpoint a knot's identity.
And the best part, there's a way to actually calculate these special characterizing slopes using some pretty cool tools from hyperbolic geometry.
So let's unpack that a bit. The paper starts by establishing that these characterizing slopes exist for any given knot. What exactly do we mean by characterizing slope?
So imagine you've got two different knots, and you perform Dehn surgery on both of them using the same characterizing slope. If you end up with the exact same three-manifold, well, then you know for sure that those two knots were actually the same knot all along.
It's like a fingerprint, a unique identifier for the knot.
Exactly. And what's really cool is that Sorya and Wakelin didn't just prove these slopes exist, they went a step further to actually calculate a bound for these slopes. For any knot you give me, I can use this formula to calculate a value called CK.
So this CK is like a threshold. Anything beyond that, and we're in characterizing slope territory.
Precisely. Any slope with a denominator larger than CK is guaranteed to be a characterizing slope. No need to test every single slope. We've got a clear cutoff point.
That's incredibly useful. So how does this formula actually work? What are the key ingredients that go into calculating this bound?
Well, it all hinges on something called the JSJ decomposition, which is a way to break down a knot's exterior, the space around it, into simpler pieces. These pieces can be either hyperbolic or Seifert-fibered.
For those who might not be familiar, can you give us a quick rundown of what those terms mean?
Sure. Hyperbolic spaces are kind of like saddle shapes. They have constant negative curvature. Seifert-fibered spaces, on the other hand, are built by gluing together simpler pieces in a specific way, creating a sort of twisted bundle structure.
Interesting. So does the formula use both types of pieces, or does it focus on one in particular?
It primarily focuses on the hyperbolic pieces because they tend to hold more useful geometric information when it comes to characterizing knots.
Makes sense. So what information from these hyperbolic pieces does the formula use?
There are three key geometric constants that come into play, QK, RK, and SK, each capturing a different aspect of the hyperbolic structure.
Let's break those down one by one. Starting with QK, what does that represent?
QK is directly related to the shortest geodesic in a specific hyperbolic piece of the knot's exterior.
Geodesic meaning the shortest path between 2 points.
Exactly. So QK is basically measuring how tight the hyperbolic structure is in that piece. The shorter the geodesic, the tighter the structure.
Makes sense. What about RK? What does that tell us?
RK has to do with the lengths of meridians within the hyperbolic pieces. Imagine drawing a loop around each component of the link corresponding to a hyperbolic piece. Those loops are your meridians.
So RK is capturing how thick the hyperbolic structure is around those components.
Precisely. The formula for RK takes into account the maximum length of these meridians, giving us another piece of the geometric puzzle.
And lastly, we have SK. What does that one represent?
SK looks at the shortest geodesics in all the non-outermost hyperbolic pieces, basically the ones that aren't directly next to the boundary of the knot's exterior.
So it's taking into account the geometric influence of all the hyperbolic pieces, not just the most prominent ones.
Exactly. It adds another layer of complexity and robustness to the bound calculation. And it's the interplay of all three of these constants, QK, RK, and SK, that allows the formula to accurately capture a knot's geometry and determine its characterizing slopes.
This is fascinating stuff. Now, the paper also delves into a special case involving satellite knots, particularly those with a winding number of 0. Can you explain what winding number means in this context?
So picture a satellite knot as one knot kind of wrapped around another knot. The winding number tells us how many times it wraps around. A winding number of 0 means the wrapping doesn't link with the core knot in a certain way.
So what makes this special case of satellite knots with winding number 0 so interesting when it comes to characterizing slopes?
Well, it turns out that in this case, we can actually establish an even tighter bound for the characterizing slopes.
Mm.
And to do this, the paper introduces the concept of splicifiable knots.
Splicifiable knots. What are those?
A knot is splicifiable if it can be untangled or unknotted through a specific type of modification called a Rolfson twist. Basically, you cut the knot open, introduce a precise number of twists, and then glue it back together. If you can unknot it this way, then it's splicifiable.
So splicifiable knots have this unique property of being able to be untangled in this specific way.
Exactly. And this property becomes really useful when we're dealing with satellite knots with a winding number of 0, because it allows us to derive a more precise bound for the characterizing slopes.
This is all incredibly insightful. We've covered a lot of ground already, from the basic concept of characterizing slopes to the formula for calculating their bounds, and even this special case with splicifiable knots. It's amazing how these techniques provide such a powerful lens through which to study knots.
It really is.
Yeah.
And we're just getting started. Welcome back to our deep dive into characterizing slopes. Last time, we laid the groundwork talking about Dehn surgery, those special characterizing slopes, and that formula Sorya and Wakelin developed to calculate a bound for them.
And now, we're going to roll up our sleeves and dive into the nitty-gritty, the proofs. Don't worry, we'll try to keep it as painless as possible. We're not going to get bogged down in every single detail, but we want to give you a good sense of how these characterizing slopes actually work.
Exactly. The goal is to understand why these slopes are so special and how the researchers actually proved their results.
So the paper kicks things off with Theorem 1.2, which focuses on prime knots whose exteriors aren't entirely ciphered-fibered. Why this specific focus?
That's a great question. See, characterizing slopes for hyperbolic knots where the entire exterior is hyperbolic, those had already been studied pretty extensively. So Sorya and Wakelin, they wanted to expand those results to a broader class of knots, specifically ones that have at least one hyperbolic piece in their JSJ decomposition.
So they're building on existing knowledge and pushing the boundaries a bit further. Now, the proof for this theorem hinges on showing that if you have a slope with a large enough denominator, any homeomorphism between the three manifolds you get after doing surgery on two different knots using that same slope has to preserve what they call the surgered pieces. Can you break that down for us?
Sure. So the surgered piece is the specific JSJ piece of the knot's exterior that contains the surgery curve, the curve along which we're performing the Dehn surgery. Essentially, what they're proving is that if you get the same three manifold after doing Dehn surgery on two different knots using a sufficiently large denominator slope, then the way those three manifolds are mapped onto each other has to respect those surgered pieces. And they can't be mixed up.
Okay, so it's like the mapping has to maintain the integrity of those surgered pieces.
Exactly. And because those surgered pieces contain key information about the original knots, if they have to be mapped directly onto each other, well, it strongly suggests that the original knots themselves must have been the same all along.
It's like a domino effect. If the three manifolds are the same, and the surgered pieces have to be the same, then the original knots must also be the same. Now, the proof then breaks down into a bunch of different cases based on what kind of JSJ piece is present in one of the knots. What's the reasoning behind this case-by-case approach?
Well, they're considering all the different possibilities for this JSJ piece, which they call Y. It could be the exterior of a torus knot, or what's called a composing space, or a cable space, or a hyperbolic space. They analyze each of these scenarios.
So they're meticulously going through all the options for this piece.
Exactly. And for each of these cases, they show that if you assume a large denominator slope, you run into contradictions. Like, if Y were the exterior of a torus knot, the three manifold you end up with wouldn't have any JSJ tories, which contradicts our initial setup.
It's a process of elimination, ruling out possibilities until they arrive at the key scenario where Y is a hyperbolic piece.
Right. By systematically eliminating those other options, they zero in on the case where the unique characteristics of hyperbolic geometry really come into play.
Okay, so let's dive into this hyperbolic case. What makes it so special, and how does it help prove that those large denominator slopes really do work as characterizing slopes?
The key insight here is that when you have a hyperbolic Y and you perform Dehn surgery with a large denominator slope, the core of that filled solid torus, the hole you're filling in, becomes a really short geodesic in the resulting hyperbolic three-manifold.
Geodesic meaning the shortest path, right? Like we talked about before.
Exactly. It becomes this tightly stretched shortest path in the hyperbolic three-manifold. And here's where a crucial result from hyperbolic geometry comes in. If you have two hyperbolic three-manifolds that are homeomorphic, meaning they have the same topological structure, their shortest geodesics must be the same length.
So it's like a fingerprint match. If the shortest geodesics are the same length, that's strong evidence that those hyperbolic pieces are essentially the same.
Exactly. So if we have two different knots, one with a hyperbolic surgered piece, and they both give us the same three-manifold after Dehn surgery with a large denominator slope, then the other knot surgered piece must also be hyperbolic, and its shortest geodesic has to match in length.
That makes sense. But how do we know that shortest geodesic isn't matching the length of a geodesic in some other hyperbolic piece of that other knot?
That's where the detailed analysis of the hyperbolic geometry comes in. Sorya and Wakelin show that for these large denominator slopes, the shortest geodesic in that surged piece is so short that it simply can't match the length of any geodesic in any other hyperbolic piece.
It's a length comparison that seals the deal. The shortest geodesic is so unique it acts like a distinguishing feature.
Precisely. And that's the heart of their proof for the hyperbolic case. They combine clever topological reasoning with these unique properties of hyperbolic geometry to establish this critical length inequality, and that ultimately forces those surged pieces to be mapped directly onto each other.
Wow, that's amazing. They've woven together these different mathematical concepts to create such an elegant and convincing proof.
It really highlights the power of mathematical reasoning and how different areas of math can come together to solve these intricate problems.
This deep dive into the proofs has been so insightful. We've gone from this general understanding of characterizing slopes to a much deeper appreciation of the mathematical tools that make them work. And we're back for the final part of our deep dive into characterizing slopes. We've covered a lot of ground so far, delving in some pretty intricate proofs.
But now we're going to shift gears a bit and focus on that special case we touched upon earlier, satellite knots with a winding number of 0.
Right, where things get even more precise. Remember, we're talking about knots wrapped around other knots, and the winding number tells us how many times that wrapping happens.
Exactly. And when the winding number is 0, it means the wrapping doesn't link with the core knot in a particular way. This opens up some really interesting possibilities, and that's where the concept of splicifiable knots comes in.
If I recall correctly, a knot is splicifiable if we can essentially untangle it by performing a Rolfson twist.
Right. You got it. It's like a special kind of knot surgery. You cut the knot open, add a specific number of twists, and then glue it back together. If you can turn it into an unknot that way, then it was a splicifiable knot to begin with.
And the paper calls the number of twists you need to add the null homologous Rolfson twist coefficient.
Precisely. And this coefficient is really important because it directly influences the bound for characterizing slopes in this special case.
So how does knowing a knot is splicifiable help us get a tighter bound on those slopes?
Well, remember, we're trying to find a threshold, a value where any slope with a denominator larger than that threshold is guaranteed to be a characterizing slope.
Right, like a clear cutoff point for identifying the knot.
Exactly. And for splicifiable satellite knots, this threshold is directly linked to the maximal null homologous Rolfson twist coefficient of the companion knot.
The maximal coefficient. So there could be multiple twist coefficients that work.
There could be. For instance, a knot might be splicifiable using 2 twists or 5 twists. The maximal one is just the largest number of twists that still gets you an unknot.
Ah, so it's like we're looking for the strongest splicifiability property.
Precisely. And what the researchers proved is that this maximal twist coefficient is the key to determining the bound for characterizing slopes in this specific scenario.
So in these cases, we can potentially get even more precise results than with the general formula.
Absolutely. And what's even more remarkable is that sometimes this refined bound is the best possible bound. It's optimal. We can't get any tighter than that.
That's pretty impressive.
Yeah.
It really shows the power of understanding the specific geometric properties of a knot.
It does. And the paper actually provides some great examples of this in action.
Oh, can we talk about some of those? I always find it helpful to see how these concepts actually play out.
Absolutely. One example they give involves a satellite knot where the companion knot has a very large signature. This signature is a property that basically prevents it from being unknotted by a single Rolfson twist.
So it's not a specifiable knot in this case.
Exactly. And because of that, the researchers can use other geometric properties to deduce that any slope with a denominator larger than a certain value will be a characterizing slope. In this particular example, they find a bound of 34.
Interesting. So even though it's not splicifiable, they can still leverage other geometric information to get a precise bound.
Precisely. And knowing it's not splicifiable actually helps them get a much better bound than they would have gotten using the general formula alone.
So understanding those nuances of a knot's geometry can really pay off.
Absolutely. And they provide other examples too involving satellite knots, where the companion knot is either composite, meaning it can be broken down into simpler knots, or fibered, meaning it has a specific kind of twisted bundle structure. And in these cases, they can also derive these refined bounds using similar techniques.
Wow, this has been quite a journey. We've explored Dehn surgery, delved into some pretty complex formulas and proofs, and even uncovered this special case with specifiable knots. It's amazing how much we can learn about a knot's identity through these methods.
It really is a testament to the power of geometric thinking in knot theory.
Absolutely. And it leaves us with so many exciting avenues to explore. What other geometric properties could influence characterizing slopes? Are there even tighter bounds out there waiting to be discovered?
Who knows? But it's definitely something worth pondering.
This has been a fascinating deep dive into the world of characterizing slopes. We've learned how we can use Dehn surgery to pinpoint a knot's identity, and how a deep understanding of geometry can lead to incredibly precise results. We hope you've enjoyed this exploration as much as we have. Welcome back for another deep dive.
Yeah.
Today we're going to be tackling a really cool problem in knot theory.
Go ahead.
It's all about figuring out when a knot is truly unique based on what happens when we do Dehn surgery on it.
Right.
So kind of a big question in knot theory.
Yeah, it's fascinating, isn't it? You start with a knot,
Right.
carefully perform Dehn surgery along a specific slope,
Yeah.
and you end up with a new three-manifold.
Right.
And the challenge is to determine whether that resulting manifold could have come from any other knot.
Yeah, that's a good point. And that's where this concept of a characterizing slope comes in.
Right.
Can you remind us what that means?
Yeah, essentially a characterizing slope is like a unique fingerprint for a knot.
Okay.
So if we perform Dehn surgery along a characterizing slope, the resulting manifold acts like a label telling us exactly which knot we started with.
Right.
No other knot, when surgered along the same slope, would produce a homeomorphic manifold.
So it's like having a special key that unlocks only one specific door,
Uh-huh.
even in a giant warehouse full of doors.
That's a great analogy.
Yeah.
And the paper we're looking at today by Sorya and Wakelin
Okay.
tackles this problem of finding these characterizing slopes.
Right.
They build upon some impressive work by Lackenby and McCoy, aiming to develop a method for determining when a given slope is guaranteed to be characterizing for a particular knot.
So they're trying to figure out how to know for sure.
Exactly.
Yeah.
It's like a recipe or a set of guidelines to say, okay, if you follow these steps, you can be certain that the Dehn surgery you perform will reveal the true identity of your knot.
And I see they introduced this idea of a magic number,
Yes.
denoted by CK,
Yeah.
that seems to play a key role.
Yes, CK is a crucial element in their approach.
Okay.
They show that if the denominator of our surgery slope, denoted by the absolute value of Q, is larger than this CK, then that slope is guaranteed to be a characterizing slope for the knot K.
Okay, so CK is like a threshold. Cross it, and you're in the safe zone, knowing that your Dehn surgery will produce a manifold that uniquely identifies your knot.
Precisely. It's like having a guarantee,
Yeah.
a mathematical certainty that you've found that unique fingerprint.
But how do they even begin to calculate this magic number? It seems like a daunting task.
Well, they cleverly leverage a powerful tool called JSJ decomposition.
Okay.
Essentially, they take the knot's exterior, the space surrounding the knot, and break it down into simpler pieces, each with its own specific geometric structure.
So they're kind of dissecting it.
Yes, it's a bit like dissecting a complex machine to understand its individual components.
So they're looking for patterns or properties within these individual pieces
Exactly.
that might reveal when a slope becomes characterizing.
Precisely. And there are four main types of JSJ pieces that can arise.
Okay.
Torus knots, cable links, composing links, and hyperbolic links.
Okay, so four main types.
Yes, and interestingly, Sorya and Wakelin had already tackled the problem for the first three types in their previous work.
Okay.
So this paper focuses on the most challenging case, hyperbolic links.
So they're venturing into the wilds of hyperbolic geometry.
Uh-huh. Yes, you could say that.
Armed with JSJ decomposition as their guide.
Mm-hmm.
What's their main weapon in this battle for characterizing slopes?
Their main weapon is Theorem 1.2.
Okay.
It establishes a concrete connection between the geometry of these hyperbolic JSJ pieces and the denominator of the surgery slope. absolute value of Q.
Uh-huh.
They define three constants,
Yeah.
QK, RK, and SK,
Okay.
each capturing a different geometric aspect of the hyperbolic pieces.
Okay, let's break those down.
Sure.
What do these constants represent, and how do they relate to that magic number, CK?
Certainly. QK is associated with the shortest geodesic, also known as the systole,
Right.
of the outermost hyperbolic JSJ piece.
Mm-hmm.
Think of it as the tightest loop you can draw within that piece. The shorter the systole, the more tightly wound that piece is.
So QK is a measure of how compact that outermost hyperbolic piece is.
Yes, geometrically speaking.
How about RK?
RK is determined by the lengths of meridians on the boundaries of those hyperbolic pieces.
Okay.
You can picture a meridian as a loop that runs around the waist of each piece.
Mm-hmm.
RK gives us information about the relative sizes of those pieces compared to their boundaries.
Interesting. So RK is telling us about the relationship between the interior and exterior of these hyperbolic pieces.
Precisely.
And lastly, what about SK?
SK is similar to QK, but with a broader perspective.
Right.
Instead of focusing only on the outermost hyperbolic piece, SK considers the shortest geodesics of all hyperbolic JSJ pieces.
Got it.
It's a measure of how tightly wound the entire hyperbolic structure is, taking all the pieces into account.
So we have these three geometric constants, each providing a different lens through which to examine those hyperbolic pieces.
Exactly.
How do they combine to give us CK?
That's where Theorem 1.2 comes into play. It states that CK is simply the maximum of these three constants, QK, RK, and SK.
So the magic number is determined by whichever geometric feature is most extreme, so to speak.
Precisely.
If any of those features are particularly pronounced,
Yes.
it pushes the threshold for a characterizing slope higher.
Exactly. And the beauty of this theorem is that it provides a practical way to calculate CK for any hyperbolic knot.
Okay.
You can use software tools like Snappy
Mm-hmm.
to determine the systoles and meridian lengths.
Right.
Then simply take the maximum.
That's incredibly useful.
Yeah.
But Theorem 1.2 isn't just about providing a formula.
Right.
It also makes a profound statement about the relationship between these geometric constants and the behavior of depth surgery, right?
Absolutely. The core of the theorem lies in the fact that if the absolute value of Q, the denominator of our surgery slope, exceeds CK, then any homeomorphism between the surgered manifolds must respect the original JSJ decomposition.
Hold on, let's unpack that a bit. What does it mean for a homeomorphism to respect the JSJ decomposition?
It means that the homeomorphism can't just mix and match those JSJ pieces arbitrarily.
Okay.
Surgered pieces from the original manifold must map to surgered pieces in the resulting manifold. They can't be shuffled around or rearranged in a way that violates the original decomposition.
So it's like saying that if you have two identical Lego models and you swap a few bricks, you can't just stick them anywhere you like.
Right.
You have to replace them in a way that maintains the original structure.
Exactly. And this restriction is crucial for proving that the slope is characterizing.
Okay.
If the homeomorphism were allowed to jumble the pieces, it would be much harder to guarantee that the resulting manifolds could only come from one specific knot.
I see. So this restriction on the homeomorphism is like a set of rules.
Yes.
That prevents too much Krieg of freedom when comparing those surgered manifolds,
Exactly.
making it easier to pinpoint a unique knot.
Precisely. And this restriction stems directly from the fact that the absolute value of Q is larger than CK.
Okay.
The geometric constraints imposed by those constants, QK, RK, and SK, are what ultimately enforce this crucial property of the homeomorphism.
This is fascinating. It seems like Theorem 1.2 is not just a formula, but a deep insight into the interplay between geometry and topology in the context of Dehn surgery.
It is. And it's this insight that allows us to pinpoint those characterizing slopes and confidently declare that a particular Dehn surgery truly defines a unique knot.
This is truly a remarkable result.
So are you ready to see how these theoretical tools work in practice?
Absolutely. I'm always eager to see how abstract concepts translate into concrete examples. So it's like watching a blueprint come to life as a building. What kind of examples do they provide?
They offer a range of fascinating cases, but let's start with example 5.1.
Okay.
It involves a rather intricate knot denoted as BW3031 41 tag 61.
Wow, that notation already hints at a complex structure. Can you break down what that represents?
Certainly. It's a satellite knot, which, as we discussed earlier, means it's constructed by wrapping one knot around another.
Right.
In this case, the pattern knot is a Borromean rings configuration.
Okay.
It's then spliced with the Whitehead double of the right-handed trefoil and the connected sum of the figure 8 and stevedore knots. Quite a mouthful indeed.
That's a lot to visualize. It sounds like a knotting masterpiece with multiple layers of complexity. How do they even begin to calculate those constants Q, K, R, K, and S, K for such an intricate knot?
That's where Snappy comes in handy.
Okay.
It's a powerful software tool specifically designed for analyzing the geometry and topology of knots and three manifolds. Sorya and Wakelin use Snappy to determine the relevant geometric properties of this knot, ultimately leading to the calculation of those constants.
So Snappy is like a high-tech toolkit for knot theorists, allowing them to explore the hidden structures within these intricate mathematical objects. What values do they find for those constants?
For this particular knot, they find that QK is 34,
Okay.
RK is 2, and SK is 25.
And since CK, that magic number is the maximum of those three values.
Right.
It ends up being 34 in this case.
Exactly. Which means any Dehn surgery performed on this knot along a slope whose denominator is greater than 34 will produce a manifold that uniquely identifies this knot. No other knot, when surgered along the same slope, will result in a homeomorphic manifold.
That's incredible. It's like finding a needle in a haystack.
Yes.
But instead of searching randomly, we have this precise geometric guidance thanks to CK. It tells us exactly where to look to guarantee that our Dehn surgery captures the essence of this unique knot.
It's a remarkable testament to the power of combining theoretical insights with computational tools. And this is just one example. Sorya and Wakelin provide several others showcasing the versatility of their approach across a variety of knot structures.
I'm already impressed.
Yeah.
But they also point out some interesting nuances in special cases like Remark 5.2, which deals with cabling a knot. Can you remind us what cabling entails and what insights they offer?
Certainly. Cabling involves taking a knot and essentially twisting another knot around it, creating a new, more complex knot. Imagine taking a thin rope and wrapping it tightly around a thicker one.
So it's like adding another layer of entanglement to an already existing knot.
Yeah.
Does this cabling process change the magic number CK for characterizing slopes?
That's the interesting part. Remark 5.2 highlights that cabling a knot doesn't actually change CK.
Oh.
The reason is that the outermost piece in the JSJ decomposition becomes what's called a cable space, and the contribution of this cable space to CK is already accounted for in the original calculation.
So it's like adding a new room to a house, but that room is already included in the overall blueprint. So the total area doesn't change.
That's a great analogy. It emphasizes that the calculation of CK cleverly captures the essential geometric features that determine characterizing slopes, even when we introduce additional complexity through cabling.
I'm starting to appreciate the depth of this magic number. Now, what about Remark 5.4? It seems to focus on twisting a link component.
Right. Remember that in the JSJ decomposition, we break down the knot's exterior into various pieces, some of which might be links.
Okay.
Remark 5.4 explores what happens when we twist one of the components of these links.
So imagine taking one of those interconnected loops within the JSG decomposition and giving it an extra twist.
Yes.
Does that affect those characterizing slopes?
It can, but in a subtle way. Twisting a link component doesn't alter the systole, which, as you recall, is the shortest geodesic within a hyperbolic piece.
Right.
So QK and SK remain unchanged.
But something must be affected. Otherwise, they wouldn't have included this remark. What changes?
The change occurs in the meridian length.
Okay.
Remember that RK is determined by these lengths, and twisting a link component can actually alter them.
So it's like tightening a knot in one spot might make the loop around another spot longer, even though the shortest path through the entire knot remains the same.
That's an excellent analogy. It highlights the interconnectedness of these geometric features. Even a seemingly localized change, like twisting a single link component, can have ripple effects on other aspects of the geometry, potentially influencing RK and consequently CK.
This is all starting to make sense. We have these geometric constants, QK, RK, and SK, each capturing a different facet of the knot's structure.
Yes.
And even subtle modifications to the knot can shift those values, ultimately affecting those crucial characterizing slopes.
Exactly. And the beauty of Sorya and Wakelin's work is that they've provided a framework that not only allows us to calculate these constants, but also understand how they relate to each other and to the broader problem of characterizing knots via Dehn surgery.
Now, earlier you mentioned that for certain satellite knots with winding number 0, a new constant TK comes into play. It's related to splicifiability, which sounds intriguing. Can you elaborate on that?
Of course. Splicifiability is essentially a measure of how easily we can untangle the companion knot in a satellite construction using a specific type of move called a Rolfson twist.
So it's like having a magic wand that can untangle certain knots with a specific flick of the wrist. But instead of magic, we have these precisely defined Rolfson twists.
That's a vivid way to put it. And TK quantifies this untangling potential. It represents the maximum number of null homologous Rolfson twists we can perform on the companion knot while maintaining certain properties of the satellite construction.
Null homologous, that sounds like a technical term.
It is.
Can you remind us what that means in this context?
Certainly. In knot theory, we often represent knots and links algebraically using what are called homology groups.
Right.
These groups capture the fundamental loops and holes within these topological objects. A null homologous Rolfson twist is essentially a twist that doesn't change the overall homology structure of the knot. It's like rearranging the furniture within a room without altering the walls or doorways.
So TK is telling us how much we can rearrange the companion knot without fundamentally changing its topological S.
Precisely. And it turns out that this rearrangement potential has a direct impact on those characterizing slopes, particularly in those special cases of satellite knots with winding number 0.
How so? How does this TK connect to those crucial slopes?
It's all about controlling the behavior of homeomorphisms between those surgered manifolds.
Okay.
Remember that to guarantee a characterizing slope, we need to restrict how those homeomorphisms can map the JSJ pieces.
Right. They can't just shuffle the pieces around willy-nilly. They have to respect the original decomposition.
Exactly. And it turns out that if TK is large, meaning the companion knot is highly tangled and requires many Rolfson twists to unknot, it becomes more difficult to find a homeomorphism that swaps those JSJ pieces.
So in a way, a highly tangled companion knot is acting like a safeguard,
Yes.
making it harder to fake a characterizing slope using some clever rearrangement of those JSJ pieces.
That's an insightful way to think about it, and that's why TK plays such a crucial role in Theorem 1.8. It ensures that if absolute value of Q, the denominator of our surgery slope, is greater than both 2 and TK, then we can rule out those troublesome homeomorphisms that might try to swap the pieces.
It's like TK is setting up a barrier, saying, if you want to swap those pieces, you'll need a really large denominator in your surgery slope to overcome this entanglement.
Precisely. And this restriction on the homeomorphism then leads to the conclusion that the slope must be characterizing, just like in the more general case of Theorem 1.2.
I'm starting to see the elegance of this approach. They've identified these key geometric and topological features captured by those constants QK, RK, and TK, and shown how they govern the behavior of Dehn's surgery, ultimately leading to those characterizing slopes that reveal the unique essence of a knot.
It's a beautiful example of how seemingly abstract concepts can have very concrete consequences, providing powerful tools for unraveling the complexities of knot theory.
This has been an incredibly insightful discussion, but I'm curious to see how this all plays out in those cases where the bounds provided by these theorems might not be optimal.
Yeah.
They hint at this in the paper, suggesting that there might be even sharper magic numbers lurking out there.
That's an excellent point, and that's where we'll pick up in our next segment.
Okay.
We'll delve into the concept of optimal bounds, explore those intriguing cases where TK might be greater than or equal to QK, and see how those multi-clasped Whitehead doubles reveal the sharpness of these results.
So we've established these really powerful tools for determining characterizing slopes based on these geometric constants.
Right.
But now I'm curious about those cases where the bounds provided by these theorems might not be the sharpest possible.
Yeah.
It seems like there's potential for even more refined insights there.
You've hit on a crucial point.
Yeah.
While Sorya and Wakelin's theorems provide general guidelines that work across a wide range of knots, they acknowledge that in certain cases their bounds might not be optimal, meaning there might be characterizing slopes lurking out there with denominators smaller than what their theorems guarantee.
So it's like having a map that guides you to a treasure. But the map might be a bit oversized, suggesting a larger search area than necessary.
Yeah.
There might be a more precise map that pinpoints the treasure with even greater accuracy.
That's a great analogy. And the quest for these optimal bounds leads to some fascinating territory within knot theory.
Right.
One particular scenario that highlights this potential for sharper bounds involves situations where that constant TK related to splicifiability is greater than or equal to QK, the systole of the outermost hyperbolic piece.
That sounds intriguing. What happens when TK surpasses QK? Does it overturn those previous theorems?
Not at all. Those theorems still hold true.
Okay.
They might not be telling us the whole story.
Right.
Corollary 5.14 specifically addresses this scenario.
Okay.
It states that when TK is greater than or equal to QK, the bound provided by theorem 1.8, the one dealing with winding number 0 satellite knots, is actually the best possible bound we can achieve.
So in those cases, we know for sure that no smaller denominator in the surgery slope can guarantee a characterizing slope.
Exactly.
It's like hitting a fundamental limit.
It's like reaching a point where the untangling potential of the companion knot measured by TK
Right.
becomes so dominant that it dictates the sharpest possible boundary for characterizing slopes.
And this is where those multi-clasp Whitehead doubles come into play, right?
Precisely.
They provide concrete examples of this optimality.
Example 5.15 in the paper showcases this beautifully.
Yeah.
They construct specific examples of multi-clasped Whitehead doubles of double twist knots and demonstrate that in these cases, the bound provided by theorem 1.8 is indeed the best possible.
Okay.
No smaller denominator in the surgery slope can achieve that guaranteed uniqueness.
So these multi-classed Whitehead doubles are like those edge cases that reveal the true power and precision of these theorems,
Yes.
pushing them to their limits.
Exactly. They're like those stress tests that engineers perform to ensure a bridge can withstand extreme conditions.
Right.
They highlight the robustness of those mathematical bounds, showing that they hold firm even in those challenging scenarios.
I'm really impressed by the level of detail and rigor in Sorya and Wakelin's work.
Yeah, me too. It's really well done.
They've not only established these powerful general theorems, but also explored those subtle nuances and edge cases that reveal the depth and beauty of this area of knot theory.
It's a testament to their deep understanding of the interplay between geometry and topology.
Yeah.
They've provided a framework that not only solves a specific problem,
Right.
but also opens up new avenues for exploration and discovery.
And for our listeners, this is where the real excitement begins. Sorya and Wakelin have charted a course, but there's still so much uncharted territory. They've shown us that while these bounds are powerful, they might not always be optimal. That leaves open the tantalizing possibility of discovering even sharper magic numbers out there, potentially hidden within those unexplored corners of knot theory.
It's an invitation to dive deeper into the intricate world of knots, to explore those subtle geometric and topological features that might lead to even more refined insights into those characterizing slopes.
So we encourage all of you to check out the full paper experiment with those examples in Snappy, and perhaps even embark on your own quest to uncover those hidden magic numbers that govern the uniqueness of knots. Until next time, keep exploring the infinite depths of knowledge.